Now this program is all about beams and triangles and trusses, the kind that you see on railway bridges. And you might well ask, what does a vulture have to do with a railway bridge? Well, remember it. It's going to provide us with a great lesson before this half hour is over. In the first two programs of this series, I nattered on about the loads that a structure has to put up with and the pushing, pulling, twisting and bending that results. Now it's time to look in more detail at just how a structure does handle those loads and at some of the structures that do it differently to others. Now it may not seem obvious, but the best place to start is with the roof over our heads. You see, when you think about it, a solid roof over one's head is the prime requirement for any civilized existence. Without roofs, there'd be no permanent buildings. Without buildings, there'd be no settlements, no cities, well, there's no need to go on, is there? But the problem is, permanent roofs are heavy, and finding ways of holding that roof up there goes right back to the beginnings of civilization itself. In fact, it's quite probable that we needed roofs long before we needed walls. When we look at a famous building, or for that matter, any building, it's always very sobering to realize that the way the architect has solved the roofing problem affects more than just the look of the roof. It affects the walls, the openings in those walls, and in fact, the whole design of the building. So starting a building from the top down may sound silly, but in fact, it makes a great deal of sense. There are lots of possible approaches to the design of a roof structure. Let's look at some of the early ones. If we go back to the Roman and Byzantine empires, we'll see that almost all the roofs are sloped. But the problem is that as gravity pulls the weight of a roof down, it means that the sloped roof pushes outwards vigorously. Here's an easy way to demonstrate that fact. These two young people are forming a sloping roof in 2 dimensions. Now, whilst they're on solid ground, nothing much happens, but we've actually cheated. They're standing on skateboards, and we're holding them in place with our feet. Look what happens when we pull our feet away. Are you ready, guys? We'll catch you if anything happens. Okay, pull the supports. Oh, thanks, guys, that's great. So, whilst a sloping roof may look elegant, it does have some problems. It pushes outwards. There is another simpler and cheaper way to hold up a roof. We can use a flat beam of one sort or another. And horizontal beams don't push outwards. So let's move from the great buildings of the past to a simple log cabin. Look up at the ceiling. You see that it is spanned with long beams, or joists as they are called. They take the weight of the roof right out to their ends and then transfer it vertically down into the walls without pushing sideways and outwards at all. And because of that, and the fact that the roof doesn't push the walls outward, the beam is one of the most important devices in structural engineering. And in fact, the application of the beam extends far beyond the roofing of buildings. The word beam in Old English just meant tree, and at first that's all they were. Just dirty great tree trunks. But the supply of large trees was not unlimited, and there came a time when the supply of large trunks, or at least for structural purposes, was scarce. The problem then became, how do you construct a big roof from a short length of timber? Well, there is one fairly obvious solution to the problem. You can lean 2 pieces up against one another. But just like the Roman roofs, this kind of structure starts to push out. We could resist that by making very thick walls or by applying some tension, just putting something across the bottom. Here we are back again with our young experimenters. And just as before, they're leaning together and we've got our feet behind their skateboards to stop them from falling down. And here we go again. We're going to pull our feet away. You ready? Right, now. But the skateboards didn't move and they haven't fallen down. Why? Well, this time we've tied their feet together. So, in a real roof it could be a cable or a long, thin piece of wood. Now, the fact that it's thin doesn't matter because it would only bend and break if it were in compression, whereas this would be stretched. In fact, you can use several short pieces of wood bolted together in tension. There. We've just created the simplest truss. 2 pieces of wood and a tie across the bottom. And the neat thing about it is that just like a beam, a truss pushes straight down on the walls. In other words, if we wrap the whole thing up, it would be just like a beam, in effect, a closed system. But why is it so strong? Well, if you have a square frame like this and the joints are just bolted together, when you push against it from any side, it deforms. One way to stop it from deforming is to make these joints very strong or rigid so they won't bend. The only trouble is that if there is a load that does want to make it bend, the members on the side want to deform in the middle, rather than at the joint. So the sides of the square are subjected to the most tortuous situation. The best illustration of this is what I call the ski boot syndrome. All ski boot designs are rigid. I mean, the whole point is to stop the ankle from bending sideways because it's notoriously weak in that direction. But this is where we can get another lesson from nature. You see, the ankle is a hinge. It's a natural safety joint. And nature figured that it would be much more preferable to sprain our ankle in a fall than to break our leg if push came to shove. But the ski boot keeps the ankle rigid. Well, in the early days of skiing, the result was that the leg would break just above the ankle at a point where the bone was never designed to take such stresses in the first place. So not only were there lots of breakages, they were nasty ones at that. What happened, of course, is that the safety binding has replaced the ankle. It gives way before anything else. It's a sort of mechanical substitute for the safety joint of the ankle. Well, if we go back to our square, you can see that instead of making the joints rigid and giving it a case of ski boot syndrome, there is a much more elegant way out. We just put a member diagonally across the square. Now there are 2 triangles, and they are very strong. Triangles have special properties. You see, 3 sides is the smallest number you can have to enclose a space. In fact, if you fix the lengths of the sides of a triangle, it can only have one shape, only one unique set of angles at its joints. And the joints don't have to be rigid at all. They could be hinged, and the triangle would still not deform. As soon as you have more than 3 sides to a structure, you can have unwanted flexibility. But any multi-sided shape can be looked at as if it was made up of a bunch of triangles. If we put in the cross pieces to make the triangles, we get a non-deformable structure again. Delicious. And now I think that should be enough. Actually, you can make your own trusses with these popsicle sticks, or coffee stirrers as they're sometimes called. If you wish, you can use bigger ones. These are tongue depressors that the doctor sometimes has. And paper fasteners that work something like this. You just push them through, bend them over the other side. Oh, of course, you have to make holes in the sticks first. Now, this is the simplest truss, and it's called the A truss. And what it has is a collar or
tie beam across the bottom. This simple device gives us many advantages over those original long poles. For instance, we could raise the collar a bit to give some increased headroom above the tops of the walls. Mind you, better not go up too high, otherwise you start to push out again. Of course, there are many other sorts you might like to experiment with. We're going to be looking at many of them later in the programme. But first, I want to demonstrate one more advantage of the truss. You see, it is in effect a very deep beam, and that means it can take much heavier loads on the roof. Look, this is what I mean. The deeper a beam is, the more effective it is. For instance, I could take this ruler and lay it flat between these supports, but it will not support as much in the middle as it would if I put it on its edge. In other words, its geometry, or in this case its depth, has been increased to make the beam more effective. So, to sum up, the truss itself is a very deep beam, which means it can take heavier loads on the roof, and, most important of all, it pushes directly down on the walls, not outwards.
Now, this simple idea was actually developed in late Roman times, but it was lost in the European Dark Ages. It didn't re-emerge until the late Middle Ages, as we can see in this painting by Botticelli in 1482. It's sort of one of those things that's obvious once you've seen it. But trusses don't just hold up roofs, they hold up lots of things. Here's a great example. One of the best things about bridges is that they've got their clothes off, and you can actually see how the structure works. Buildings usually keep their clothes on, and so you can't see the structure easily. And in the design of trusses, the North American engineers of the 19th century came into their own, and for a very interesting reason. In Europe, the railways were straight and level. They usually dealt with the ups and downs by small cuttings and embankments and occasional small bridges. Victorian England, where the railway was first developed, had the necessary supply of capital and labour to build those things. In North America, conditions were very different. First of all, the terrain is rugged everywhere. And because the railroads were spanning the continent, the distances were enormous. Capital was scarce, wages were high, even for the unskilled. And in the land of the free, where everyone was an amateur, in the best sense of the word, skilled craftsmen were rare. We were a continent of jacks of all trades, masters of some. Iron was expensive, but timber was plentiful. And above all, North American railroad engineers were very willing to take risks. In fact, there are those who say that life was more hazardous to 19th century Americans because of their engineers than for any other reason. Now, simple cuttings and embankments could not be used because big valleys could only be spanned by giant timber trestles and viaducts. They were made of wood that was found on the spot. Look at some of these examples. They were sometimes made solid by dumping earth in over the timber. But when the wood rotted away, the earth remained to support the tracks. Now, these trestles were fine for spanning deep valleys as long as they didn't have a big, wide river in the bottom of them. The wood structure filled everything in and, of course, would have blocked up the river. So the need arose for very long span bridges that were cheap, easy to make, and flat, because the constant battle always was to keep the grade or slope of the track low and still keep as much clearance above the river as possible to let boats through. That set the scene for the spectacular development of the wooden truss. In fact, it all happened in just over 20 years or so, from about 1840 to 1860. In North America in 1840, the most plentiful material around was wood. Iron was available, but was expensive. The problem was this. How do you make long, flat bridge trusses using short, straight bits of timber and the minimum amount of iron rods or strapping? William Howe came up with this. You've got a top member and a bottom member and both diagonal and vertical pieces. Howe realised he had too much material and refined his truss by removing bits. The vertical members would be stretched and the diagonals would be squashed, tension and compression. Very soon, Thomas Pratt, Howe's rival in truss design, came along and said, "I think you're wrong. I think it's the verticals that should be compressed and the diagonals that are stretched." Soon both Howe and Pratt had taken more pieces out of their truss designs, but there were still more members than they needed. Well, before you knew it, along came two more elegant designs, the Bolman and the Fink trusses. They are very light because the members were nearly all cables. Now, while we don't see too many of these on bridges today, there is one place where the Fink truss is still common. The combination of cables and guy wires on the mast of a catamaran is really just a Fink truss. Back to the bridges. One final refinement was yet to be made by a Brit, James Warren. He finally came up with a bridge truss that used such a small amount of members that it could be made out of steel economically. He simply eliminated the verticals and used alternating diagonals. This is the Warren truss. So the next time you're out for a walk, take a look at the bridges. Many of them will owe their heritage to the pioneers of the last century.
This is the Lemure Island Railway Bridge across the Ottawa River. And notice how to get the most clearance above the water, the truss is above the tracks. That's just the opposite to a roof, of course, where the truss is usually underneath. But how does such a truss work? How come engineers came up with this kind of a scheme to get heavy loads across a river without the bridge breaking? Well, to understand that, we have to go back to the simple beam that we spoke about at the beginning of the programme. And we've already seen that the deeper a beam, the more load it can carry. But there's much more going on inside a beam or a truss when it's being heavily loaded down by, say, a freight train. I trust one isn't coming along just yet. I could demonstrate this to you by using this pink eraser. Now, imagine it's a beam that's spanning between my fingers there, just like a bridge across a river. And that my thumbs represent the load, say, of a freight train, or even a lot of snow. And as you can see, the top and the bottom are bending. But look a little closer at what's actually happening. The top is getting all scrunched up. It's closer together. It's being compressed. Whereas at the bottom, it's being stretched. It's in tension. Too much load, of course, and if the beam broke, it would split at the bottom, not at the top. So, in this beam, we have compression at the top and tension at the bottom. Now, that means that somewhere in between, where it's changing from one to the other, it's neither compression nor tension, and we call that the neutral axis. Now, that means, of course, that we don't need any material in the middle of the beam to do any work against the compression and tension, because there isn't any. Oh, we must have enough material to keep the top connected to the bottom, but that's all.
Out of an analysis like that came something we've all seen, the I-beam, where we've got most of the material at the top and bottom. And it's in compression at the top and tension at the bottom. And what some bright spark said was, how can we increase the effective depth of that system without changing the amount of material? And he cut it like this. Then he moved one half and put it on top of the other. And of course, you get something like this. So you've increased the effective depth from the original I-beam without adding any material. You just have to weld it there along its neutral axis. It also enables you to put pipes through the holes. From this idea, we developed the trussed beam. And that's what you see over most large open areas, such as gymnasiums. So you've got enough material to keep the top connected to the bottom, but you've put the bulk of the material where it wants to do the work, at the top and the bottom. And of course, you can see another reason why this sort of thing works so well. It's the triangle. It won't deform. I bet you thought the show was all about roofs. Well, I hadn't forgotten at all. You see, the trusses designed for bridges are predominantly flat, but we usually prefer our roofs to be sloped so they will shed the rain and snow. So, as with bridge trusses, there have been lots of designs for sloped roof trusses too. If you go up into your attic, you will most probably see one of these. And you can always tell a trussed roof from a non-trussed roof because a trussed roof has its feet tied together. There's one thing we haven't talked about in all this. It's all very well to have these wonderful trusses, but what stops them from falling over sideways? If you just stand a truss up by itself, it may be strong, but it's not at all stable. So what you have to do is join more than one truss together. Often the roof covering does that, or as we see in a bridge, you can use horizontally triangulated cross bracing. That's like a truss on its side. It can be beneath the road deck, or as in this case, above it. The ultimate derivation of this is to have a truss in more than one direction. We call such a structure a space grid, and there are lots of examples. This one is in an aircraft hangar. You can see that the roof support is a truss from right to left, but it's also a truss from front to back. And if you look at the top and bottom of the whole thing, well, there are trusses there too. But space grids are made up of different size members with complicated joints. So a further development of the space grid is the space frame or space deck. These structures can span enormous distances and enclose huge volumes without internal supports to obstruct the space beneath. Space frames are often used for large exhibitions, such as Expo 67 in Montreal. These pavilions were constructed from thousands of equal-sized members and hundreds of standardized joints. This not only means economies in manufacturing costs, it also enables the forces set up in the system to be distributed evenly and in many directions at the same time. This allows us to make large openings, for instance. There are plenty of other structural members around such an opening to do the work of the missing members. Now, these space frames at Expo 67 had many square as well as triangular patterns. A purer form of space frame uses many more interconnected triangular pyramids or tetrahedrons, increasing the triangulation throughout the system and further simplifying the joints. This is the structural system that was used for the roof of the National Aviation Museum in Ottawa. The visual impact of this roof is enhanced by using the same space frame system for the vertical supporting pillars. Now, the mathematical calculations for such a design are so complicated that they were impractical before the advent of the computer. So the overall advantage of the space frame is a very strong but much lighter and therefore more economical structure. You see, by combining the idea of a beam with the strength of a triangle, we've done a lot more than merely put a roof over our heads. By the way, it is fitting that this system has been used for the Aviation Museum. Way back in 1909, Alexander Graham Bell built the first airplane in Canada. And 2 years earlier, he also pioneered the tetrahedral space frame when he built these experimental structures. However, even this great man must take second place on this idea. Remember the vulture at the beginning of the programme? Well, now let me explain what it has to do with railway bridges, truss design and space frames in general.
Now, it only took man the last century or so to evolve all of those designs. Seems pretty clever, doesn't it? But nature did the same thing millions of years ago. This is the skeleton of a vulture, and it belongs to the Royal Ontario Museum. Take a closer look at this particular wing bone here. If we were to slice it long ways, we'd see that inside it's triangulated, just like a truss. In fact, the same thing applies to any large bird. And although this isn't the wing bone of a vulture, you can see the triangulation quite clearly. The pelvis of a bird is also triangulated like a truss. And not only that, it's identical to the simplest of roof trusses. You can see it here. But nature doesn't confine itself just to the simpler forms. You only have to look inside any bone to see that it's just like a truss in 3 dimensions. In fact, a space frame.
Well, that covers roofs over our heads, but they still need walls and columns to hold them up. And that is the subject of the next programme.